so the properties of this sum are determined by the singularities of the logarithmic derivative, that is by the pole of the zeta function, gives this term, and by the zeros of the zeta function, which gives the lower order terms in the asymptotic. So prime number theorem we have says that the error term gives its rules in x, but of course on the Riemann hypothesis it will be something like square root of x. Now, for the correlation function of the von Mangold function, there's a famous conjecture of Hardy and Littlewood in 1923. So they said that if you give von Mangold look at ordered correlations over some range of length x, the sum is proportional to x. So that is, there is an average. The correlation function defines it as the average here, so dividing both sides by x has a limit as x tends to infinity, which is non-zero, typically, and you get some function of h here, which I won't specify as an explicit formula for it. It depends on the prime factorization of the shift h. That's the famous conjecture. There's another conjecture which I'd like to focus on today, which is concerns not the sum of the von Mangold function over large ranges, but the sum over small intervals. This is a conjecture due to Dalton and Montgomery in 1987, and extended by Montgomery and Sound in 2004, as I'll explain. So here, one takes the von Mangold function and sums it over an interval containing capital H integers tends to x. Since the von Mangold function has mean value 1 on average, you expect this to give out h in size. So you subtract h and then look at the mean square of the difference with respect to the center point of the interval x. And the conjecture is that this grows, provided h is less than x, but still grows as x increases. This increases like h, the length of the interval, times log x minus log h. That was the original Dalton-Montgomery conjecture, but Montgomery and Sound introduced an additional constant term, gamma e, the Euler constant. If the primes were completely uncorrelated, they're a Poisson sequence, this would give the h. So the log of x and the log of h appear as a declaration of that, which recognizes the primes aren't completely randomly distributed. There are correlations, and those correlations are what is described by the Hardy-Littlewood conjecture. Indeed, one way to generate this conjecture, or to motivate it, is from Hardy-Littlewood. So if you take Hardy-Littlewood with a suitably precise error term, you can prove this. So if you assume Hardy-Littlewood, you can prove a mean square result for primes in short intervals, and that was the approach that Montgomery and Sound took. So this conjecture is intimately related to the Hardy-Littlewood conjecture. There's a similar conjecture for von Mangold function averaged over arithmetic progressions, and this is due to Hooley, that he announced this in 1974 in his ICM lecture. If you take the von Mangold function and sum it over some arithmetic progression a mod q, subtract off what you expect to get, which is x over the number of reduced residue classes, take the mean, take the square, and then average with respect to a, this conjecture is that you get x log q. And again, the logarithmic term there is a declaration of pure randomness amongst the primes. And this conjecture, too, you can relate to the Hardy-Littlewood conjecture, and there's a very nice paper of Dan Golston and John Friedlander, where they prove this conjecture subject to the assumption of Hardy-Littlewood with appropriately precise error terms, and they can establish this in the range where q is larger than square root of x and less than x. But for q less than square root of x, even that machinery didn't suffice, and it remained an open issue as to whether, it still remains an open issue as to what the exact range of validity of the Hooley conjecture is. Now, all these conjectures are related to another interesting conjecture, where random matrix theory comes in, and this is the Montgomery conjecture. So the idea here is that we're looking not at the statistics of the primes, but of the zeros of the zeta function. And the idea is that one takes the zeros of the zeta function, one normalizes them so they have unit mean density, so it's Tn are the height of the zeros, assuming the Riemann hypothesis, and we stretch those out by the log of Tn to counterbalance the logarithmically increasing density of the zeros, and we compare that with the corresponding statistic for, or distribution for, eigenvalues of a unitary matrix A, scaled by the size of the matrix N, so that they have unit mean spacing. And the conjecture, goes back to Montgomery, as I say, that if you look at pairs of zeros scaled in this way, and you take the limit as you go infinitely high to the critical line, then that limit exists and coincides with a matrix integral, an integral over the unitary group UN, of the corresponding statistic for the eigenvalues of the matrix A, in the limit as the matrix size tends to infinity. Conjecture, of course, is enormously profound. It is true as a spectral interpretation of the zero will be evident for a spectral interpretation. Now, the Montgomery conjecture is also very powerful because since it establishes a connection with a matrix integral, it establishes a connection with an integral that you can compute. So Dyson has already computed the integral over the unitary group on the right-hand side, and it's the famous sine kernel function that one sees now in plots. And the numerical evidence in support of the Montgomery conjecture, that is, computing zeros high for the critical line and comparing with the distribution given by the sine kernel, is really very striking. So this conjecture is intimately related to those I've already set out for the primes. This is first of all how Montgomery, Golston and Montgomery established their conjecture for the primes and short intervals, their statement is that formula they gave for the variance is equivalent to the Montgomery conjecture, so each implies the other. Likewise, one can see immediately this will be connected to Hardy-Littlewood, because if you use the explicit formula that connects the zeros of the zeta function to the primes, sums of pairs of zeros will obviously be related to sums of pairs of primes. The diagonal terms in the prime sum, where the two primes are equal, if you evaluate straightforwardly using the prime number theorem, and the off-diagonal terms, which involve looking for solutions of the equation n equals m plus h, where n and m are prime or prime powers. Well, if you want to count solutions of the equation like that, that's what the Hardy-Littlewood conjecture gives you. So if you can evaluate the pair correlation function of the zeta function using Hardy-Littlewood, and what you get is precisely the Montgomery conjecture. Of course, for certain test functions F, you don't need that, because the first test function, one knows that the off-diagonal terms don't contribute to the theorem in Montgomery's original paper. So for those test functions, Montgomery's conjecture is theorem, and really the conjecture concerns functions as discussed. That is the class where the Fourier transform has to talk in minus 1 to 1. Now, this is an aside. So this isn't the main theme of what I want to talk about. I want to emphasize that these conjectures are not restricted to pairs of primes or pairs of zeros. So all this extends to endpoint correlations, and this is a famous paper of Zev Rudnick and Peter Sarnak in 1996. A very beautiful paper that had a very significant impact on the field, is they showed that Montgomery's theorem, that is for a very restricted class of test functions, 1 and 2 pair correlation conjecture, they generalized that to all endpoint correlations. That was a major achievement. But at the same time, there's a paper I wrote with Eugene Bogomolny, which is somewhat different to the Rudnick-Sarnak paper. Theirs was beautiful and wonderfully expressed and brilliantly transparent. In mitigation, in fact, I think mitigation, Eugene and I wrote this called, I think, consciously met a single analytic number theory. So it was written very much in the language of theoretical physics, which means, well, I'll leave it to your imagination what it means. But we were able to compute something. And what we computed was the contributions from Hardy-Littlewood to all endpoint correlations, and found that they indeed match with what you would expect on the basis of random matrix theory. And I mention this because what was the sort of main idea of this paper was that you have to look not just at sort of equations of the type I mentioned for the pair correlation, where you have to count solutions of equations like n equals m plus h, where here n and m are products of prime powers. These are the analogues of the terms that contribute to pair correlation. There are other terms that come in where you have to count solutions of these systems of linear equations, such as these here, where n1 and m1, oh, I think written incorrect, there should be n2 and m2, I apologize. n1 and m1 in the top equation, n2 and m2 in the bottom equation. Where those are prime powers, or products of prime powers, and these we call type 2 octagonal contributions. And I mentioned this in passing. These won't really play much of a role in the rest of the talk, but I will come back and return to them very briefly in an aside, and I think Brian Connery will say something about this subject a little later. Another direction you can go in, which again is where Peter and Zev talked away, is to think about other L functions. So this isn't special to the Riemann-Dietz function. Their theorem extended to all principal L functions. And so the sort of questions that one asks about the von Mangold function extend to its generalizations to other L functions in the Selberg class. If F is an L function in the Selberg class, you can view it as a generating function of some arithmetic function lambda f, generated by the logarithmic derivative of f, and then it's a natural conjecture to make that the zeros of this L function will satisfy a Montgomery-type conjecture, that it will be random matrix distributed. And so if you take that philosophy, then a function like this, a sum of pairs of zeros, you can evaluate using random matrix theory, and that's what Murphy and Pirelli did. And so they conjectured that for all f in the Selberg class, this double sum of a pair of zeros will have this asymptotic form in some appropriate range. And from that, you can prove an analog, a generalization of the Dalton-Montgomery theorem. So such an assumption would allow you to prove that if you sum generalized von Mangold functions, that is, von Mangold functions associated with other L functions in the Selberg class, in short intervals, you get a similar sort of formula. You get a term that depends on the length of the range, and then a logarithmic term which recognizes correlations between these arithmetic functions. So this is a theorem I proved recently, and I mention this because I think it's not complete without interest. The proof mimics that of Dalton-Montgomery rather closely, so there's no surprises in the proof. So the slight surprise is that for many of these L functions in the Selberg class, one doesn't have a Hardy-Littlewood conjecture. In fact, one would believe that the autocorrelations of lambda f, if you sum lambda f of n, lambda f of n plus h, all the way up to x, that's little O of x. So it's very different to the Hardy-Littlewood type scenario. And I emphasize that in the Riemann case, we have quite a detailed understanding of this kind of formula coming from Hardy-Littlewood. Here, we understand it from the perspective of the zeros, but understanding it at the level of a Hardy-Littlewood type conjecture seems to me something that I personally don't understand, and seems to strike me as quite interesting. Okay, back to the main theme. I want to now look at these questions for function fields. So there's an analog of the prime number theorem for function fields, and it takes an extremely simple form. So if you get the von Mangold function associated with a polynomial f, and you average this over all monic polynomials of degree n, q to the n of these polynomials, and so if the von Mangold function has an average 1, you expect this to be something like q to the n. So the teaching fact is exactly q to the n. So one has a prime number theorem sort of on the nose with zero error term. And the point is, of course, if you mimic the usual proof of the prime number theorem, you want to write lambda f in terms of a generating function which behaves like the Riemann-Dietz function, then that function has a pole but no zeros. So one only gets the contribution from the pole, and one has nothing left to calculate from the zero. So that might lead you to think that the irreducible polynomials are in some sense too rigid, or aren't sufficiently interesting, and that one wouldn't expect interesting fluctuations of the sort that one gets from the primes. But in fact, that's not the case. And if you look at the variance in intervals, which is something I proved a couple of years ago with Brevik, so if you take the von Mangold function, which selects from the monic polynomials those that are irreducible, essentially, or their powers, and you look at the variance of a sum over some short interval whose size is positioned at a, and whose size is given by h, so the number of terms in this sum is q to the power h plus 1, and you average with respect to the center point a, then you can establish as a theorem the following limit. So you divide this by q to the h plus 1, and the limit you get is just n minus h minus 2. And the point is, this is the exact analogue of the Dalton-Montgomery conjecture. Why? Well, their conjecture, if you remember, was that this variance would be h times the log of x minus the log of h, and then a constant that Montgomery and Sound computed. Here we're dividing by h, because q to the h plus 1 behaves like h, the number of terms in this sum. So we expect to get something that's like the log of x minus the log of h. Well, the log of x behaves like q to the n, so its log behaves like n. Capital H behaves like q to the h plus 1, so its log behaves like capital H. So this is exactly the analogue of log of x minus log of h, and then there's a constant. So one has the exact analogue of Dalton-Montgomery. One also has the exact analogue of the Hooley conjecture. So if we sum the von Mangold function in arithmetic progressions, f is equal to a mod q, we expect this to be the size of the sum. Phi here is the analogue of the Euler function. So we compute the difference between the sum and its expectation, square it, and then average with respect to a, the residue class, and compute this variance. Well, this variance can be calculated. I'm going to tell you in a minute how we do the calculations, and what you get is the precise analogue of the Hooley conjecture, in that it goes like q to the n, well, that behaves like capital X, and degree of q, that behaves just like log of q. So it has precisely the analogue of Hooley. How does one prove this, these results? Well, I'll just give you the main ideas. The key idea is that if you want to average over all monic polynomials, that's straightforward, because the generating function for that is just the zeta function, and that zeta function only has a pole and no zeros, and so we can use the standard, we can mimic the techniques of analytic number theory and compute such an average. But if you want to average over subsets of the monics, which we do, we want to average over short intervals or arithmetic progressions, you can project out using Dirichlet characters. So one introduces characters to project from the sum over all and then onto some subset of that sum. So this leads to expressions involving the characters, and they twist the z function and one gets L functions appearing. These L functions do have zeros. They satisfy a Riemann hypothesis, given to us by Bay. So one can express the characteristic polynomials of the L functions in terms of unitary matrices. That is the restatement of the Riemann hypothesis in this setting. And then here's the key idea, of course. In the limit of q tends to infinity, which is the limit in which we can establish these theorems, there's a machinery, in fact it's a lean, but much developed by Nick Katz and Peter. In the case that we need it, the theorems we have were proved by Nick Katz. These sums over characters equidistribute become just matrix integrals. And then the point is that you can recognize the matrix integrals, that is, you can actually